We're going to change things up a bit now and take a look at a broader concept where we discuss classifying, this word right here. Now, how do you pronounce this word? Go ahead, try to say it. Did you say discontinuities? Well, if you did, that's not correct. It's actually discontinuities. Discontinuities. Discontinuities is a broader math concept that looks at any place which is an x value that would be undefined. Now, that certainly has a lot to do with rational functions because we know that there are some x values that we're not allowed to use. Visually, they'll show up as a break in the y value. So let's take a look at classifying discontinuities, and you'll discover it does relate to what we were discussing, but also is a little broader with some new ideas. Now, this graph, we'll call it f of x, has a lot of discontinuities. As I'm talking here, I encourage you to jot this down in your notes, to carefully copy it. As you copy it, notice how there are some places where we would clearly have x values that are undefined. There are also places where the y value breaks, and indeed these will be known as discontinuities. Go ahead and copy it down, pause the video, and I'll tell you what we're going to do with it. All right, now when you're done jotting down the graph, why don't we take a little stroll along this graph? Let's take a walk along the graph, and while doing that, I want you to think about what happens to the y values. What happens to the y values? As you think about this behavior, you're actually going to be coming up with the discontinuity. Now, the only catch here is you have to take your walk from left to right, because that's always how we approach the behavior of a graph. So start over here with me on this left side. Take a walk to the left, or from the left, and what is happening to the y value? What would you have told your neighbor? Well, you should say that the y value is going to infinity. You could say negative infinity, but the y value is going to infinity. Now, as you continue your walk, you realize that you have to somehow pass over this asymptote, and your y value, well, it's coming from infinity. It's coming from infinity. So we have our first type of discontinuity that is occurring at x equals negative 3. And simply put, that discontinuity is an infinite discontinuity. An infinite discontinuity describes what the y value is doing. And of course, that's always going to occur at a vertical asymptote. Now, what we would say is that there is an infinite discontinuity at x equals negative 3. Are you ready to continue your stroll through our graph? Because as we continue walking, we approach x equals 2. Now, when we approach x equals 2, something kind of interesting happens. How do we continue our journey? How do we move from a y value of 2 to a y value of 0? Well, the answer is simple. You have to jump. You have to jump in order to pass through this discontinuity. And so we have our next type of discontinuity, that is a jump discontinuity. Now, look at this jump discontinuity. Visually, it's pretty easy to see that you have to jump to go from y value to y value, but that's because there are two different y values. And if you have two different y values, you have a jump discontinuity. And we would say that this jump is occurring at x equals 2. Notice that we use the x value to describe the location of a discontinuity. This is a good example of why, since we would have two y values, we wouldn't know where the jump is occurring. But we don't use the y value to describe the location. Instead, we use the x value. However, the discontinuity describes what the y value is doing, and the y value is jumping from 2, y equals 2, to y equals 0. All right, well, ready to keep walking? Okay, watch your step, because as you approach our next discontinuity, it's very possible that you might fall into a hole, of course, and that's why we call this hole discontinuity. Now, we do add the word point. We like to say it's a point discontinuity. That's a little bit more specific because it describes what's happening to the y value, and the y value is missing at that point, so we have a point discontinuity. Now, notice that in contrast to the jump discontinuity, here we have the same y value as we try to pass through the discontinuity. It's the same y value versus two different y values. And by the way, I forgot to mention back here in this jump discontinuity, it really doesn't matter that there's an open circle here at the y value of 2 versus a closed circle here at the y value of 0. Whether they were both open circles or just one open circle, we would still call this a jump because, again, the y values are different. But we call this a hole or point discontinuity because the y value is the same. Now, you would say that there's a point discontinuity at x equals 4. All right, so are you having fun strolling through the graph? Because we're going to continue. And, of course, as we continue, we realize that we're approaching a horizontal asymptote. Now, I have a question for you here. As you approach that horizontal asymptote, how many times did you have to pick up your pencil? How many breaks were there in the graph? How many times was the y value missing? Well, you should say it wasn't. And that's why a horizontal asymptote is actually not a discontinuity. In fact, it kind of leads us to our last type of classification, which is really the antidote of a discontinuity. That is when the graph is continuous. You see, when a graph is continuous, it has no breaks. It has no undefined parts. And honestly, everywhere that there wasn't a discontinuity, like here, 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 all these places where there wasn't a discontinuity, we would say that the graph is continuous. But we don't give the x location for continuous because really continuous is the most common behavior of a graph. So we would say that the graph is continuous everywhere except at the discontinuities. Now, it's pretty easy to see discontinuities when you have a pretty picture in front of you, but what about if you have an equation? What I'd like to do is I'd like to add an example to each one of these discontinuities so that you can practice on how to classify and identify the type and location of a discontinuity. We always want to classify and identify the type and location of a discontinuity. So here's a function. It's a type we've seen before. It's obviously a rational function. And your eyes should be drawn to the denominator. That is the place where it's going to have an undefined x value. Remember that a discontinuity is always when x is undefined. So nothing real new here for us to say that x is not allowed to equal plus or minus 1. But what we want to realize is that that means plus and minus 1 are going to be vertical asymptotes. Of course, if there's a vertical asymptote, then there's an infinite discontinuity. And what we would say is just that. We would say infinite discontinuity, and then you would give the location, and the location is at x equals plus or minus 1. Now, again, kids will often ask, well, how'd you know it was infinite discontinuity? And my answer to that is from some prior knowledge. And the prior knowledge is, again, if there's a 0 in the denominator, that is going to be a vertical asymptote, and that is going to allow us to conclude that there'll be infinite discontinuity. And then I'm giving the location, which, of course, are both of those verticals. Let's take a look at an example of a jump discontinuity. And again, I want to do that through a equation. This equation is going to look a little different. It's actually one that that I've not shown you before. But let's approach this. First of all, uh, it's interesting. It's still the denominator that gives us our location. In fact, before I know anything else about this problem, I already know that there's going to be some type of discontinuity at x equals 0. And the reason I know that is because that's the x value that makes this function undefined. Remember, a discontinuity still relates and is an undefined x value. Now, what type of discontinuity? It's going to require a further inspection via a graph. So I encourage you with your graphing calculator to graph the absolute value of 3x over x. If you would like to do that on your own, you'll have to find the absolute value function, which is in the math menu. I'm going to show you the graph now and see how it relates to the one that you saw on your calculator. What we have here is a graph that actually seems to be two horizontal lines, but not surprisingly, at x equals 0, we have to jump. Now, I say not surprisingly. It's not surprisingly that it was at x equals 0, but what happens is we have to jump to get to the next y value. And so using a little bit of the calculator to help, we can say that there is a jump discontinuity, and it's at x equals 0. Ready to look at one more? Well, I think this one you're not going to be real surprised at, but I still want to look at it with you. A function that has a point discontinuity. And remember, a point discontinuity is the same as having a hole in the graph. And so if you look at the function that I've created here, you would quickly notice that after you factor it, that you have this common factor. You have a common factor of x plus 1. Now, again, before I even factored this and before I noticed that there was a hole, I still can look at the denominator. I want to make sure you guys understand the denominator is always where we're going to get our undefined x value. And so I actually could have said that x equals -1 is the location, but now that we identified this common factor of x plus 1, we can say that there is point discontinuity at that x value. Just by the way, this is the kind of problem that if you did graph it, which you'll be allowed to do, you're actually going to use a combination of graphing and non-graphing skills that you've learned in the past. If you did graph this one, what you would find is that there indeed is a hole in the graph at x equals -1, and the graph itself ends up being simply a straight line, and that straight line, I want you to realize, actually is the graph of x minus 1, simply because that's what's left over after we cancel out the hole in the graph. Now, a continuous graph, the truth is most graphs are continuous. Most graphs don't have any discontinuities. But I want to show you an example of a function that's a fraction, 1 over x squared plus 1, that also fits this bill. You see, if you look at the denominator of this problem, you should conclude that there is no x value that is going to give us a 0 in the denominator. Since there's no x value that's undefined, that means there's not going to be any discontinuity. In this case, the graph is going to be continuous. Now, if you do graph this on your calculator, it's an interesting graph. You end up with a graph that looks a little bit like the bell curve, but the truth is it is continuous everywhere. There is no hole in the graph. The horizontal asymptote that you're seeing here at y equals 0, that is not a discontinuity. It's a nice example of a continuous graph. All right, now here's a chance for you to try. You want to try to see if you can identify and so classify and locate the discontinuities for this function. And I encourage you to try to do it without your calculator at first. You can use a calculator to kind of help, but the truth is you might already know some of your answers just by looking at the numerator and denominator. I will go over this, but I encourage you to pause the video now so you can try to come up with the discontinuities. All right, so you're getting the idea that the denominator still gives us the location of the discontinuity. So yes, there are two different discontinuities for this problem. There's going to be a discontinuity at x equals 2, and there's going to be a discontinuity at x equals -3. Now the only thing left to do is figure out what type of discontinuity. I hope that the common factor made it pretty obvious here that there's going to be point discontinuity at x equals -3. And so the only thing left would be a jump or a vertical asymptote. It turns out that the only way you're going to get a jump is with that unique absolute value that I showed you, which means that this would have to be an infinite discontinuity at x equals 2. But as I said, you could use a graph to kind of confirm, but all you're going to find out is what we already said. That is that at x equals 2 and at x equals -3, that we have our two discontinuities. We can see the infinite behavior at x equals 2. We can also see that there is a hole in the graph, again, at x equals -3. Don't forget that if I did ask you for the y value of this hole, although I won't, but we did talk about that in previous lessons. If I asked you for the y value, you simply could plug -3 back into the equation. You would plug -3 back in to the part that has the hole canceled out, and so we'll get -1/5. But again, actually, you'll see that you don't have to give that answer. You just have to say the x location, and x equals -3 would be that spot. So yeah, you can have multiple discontinuities in one function, and that certainly is a possibility. How about a piecewise function? Piecewise functions, if you think about some of them that you've graphed in the past, you won't be surprised to say that they also have discontinuities. It's almost like that you expect to have a discontinuity of the piecewise function. Just want to go over one with you. Basically, the point or the idea here is you graph the function. If you graph it correctly, you'll be able to identify the discontinuity. But I want to show you a careful analysis of the y value. I think that that's important. So let's talk about graphing x squared plus 1. Remember, x squared plus 1 is a parabola that's shifted up 1. If you would graph, or at least think about the entire parabola, it would look like this. However, because we only want the side that is less than or equal to 0, we ultimately only get the left side of the parabola. Now, remember that if you plug in the x value, you can get the y value that goes with any function. Here, you get a y value of 1. So I just want to note that this is an important number, specifically the y value at this point. Now, if you graph the other function, you would graph x. X is, of course, a diagonal line. If you think about the whole graph, you would end up with a slope of 1 that passes through a y-intercept of 0. But of course, we only want the part that's greater than 0, so we only want the part that's to the right. Now, it's not equal to 0, so we have to draw an open circle. Now, again, a careful analysis of the y value here, you would plug a 0 into the equation, but of course, the point is already determined to be 0, 0. Now, what I'm really trying to get you to agree with and understand is that to travel along this graph and to continue traveling, we would definitely have to jump at this position. We would jump because there's two different y values. Yes, there's an open circle, but it's that the y values are different that we conclude that there is a jump discontinuity, and you can already, I hope, see that that is happening at x equals 0.